In this lesson, we'll talk about multiplication of polynomials. First, let's observe how do we multiply monomials. Remember, a monomial is a cluster of letters and numbers connected by multiplication only. So that's one monomial, and this is second monomial. And the operation between these two is multiplication. However, each monomial is also a product of letters and numbers, so we have a multiplication here and multiplication over there, and also here and also there. So this bracket is essential here only because of this negative number. We could rewrite this question by using the bracket only around -3. So we can rewrite this as a product of 2x squared y, and then -3, we need to put a bracket around the -3, but we still multiply by -3. There's no subtraction here. And then multiply by the rest, x cubed and times y to the 5. Since multiplication is commutative, we could rearrange the order of those factors. So we could write all the numerical factors first, then all factors with basis x, and then all factors with basis y. Okay, let's do it. So it will be 2 times -3. Then let's write x's together, times x squared and times x cubed. And then y's times y and times y to the 5. Now let's perform this multiplication of numbers. So we have -6. And multiplication of powers with the same basis. Remember the rule? When we multiply powers with the same basis, we need to add exponents. So keep the x and add 2 plus 3, which is 5. And then keep the y, and this is invisible 1 plus 5, so it's 6. And that will be final answer. So here I showed you every little step why we can multiply that way. However, normally we don't need to write those 2 steps. We can multiply at once. 2 times -3 and write at once is equal to -6. And then x squared times x cubed is equal to x to the 5. And then y times y to the 5 is y to the 6. So this multiplication can be actually done just in one step. Sometimes students are misled by this negative sign in the middle of the question. They try to distribute something, but there's nothing to distribute because we have only one term. And remember, the distribution property works over at least 2 terms. So here there's no distribution, it's just simply multiplication of the same type of factors. Okay, if we already know how to multiply monomials, then we can extend our skills to multiply a monomial by a polynomial. In this case, we have a polynomial with 3 terms. How do we do that? It's just by distributing this monomial to each term. So we multiply this monomial by the first term, then by the second term, and then by the third term. Therefore, we expect to have 3 terms in the end. So this question is like 3 of the previous questions. Let's focus on multiplying this monomial by the first term. The rule is, first think about sign and write it down. Since we multiply negative times positive, we write negative. Then numerical coefficients, 2 times 3 is 6. And then powers with the same basis. So x cubed times x squared is x to the 5. And y squared we need to write as well. Okay, we are ready to go to the next term. So this times this. Check the signs. Negative times negative is positive. Numerical value 2 times 5 is 10. X cubed times x is x to the 4. And y squared times y squared is y to the 4 as well. And the last term. Negative times positive is negative. 2 times 1 is 2. X cubed and y squared. In the end, we should always check for like terms. But in this case, we don't have any like terms. So that's the end of our question. Next, if we want to multiply a binomial by a binomial, 2 terms by 2 terms, basically we need to multiply each term by each term. The way to memorize what to multiply by what is the FOIL word. F stands for multiply the first terms, O stands for multiply outside terms, I stands for multiply inside terms, and L stands for multiply last terms. So FOIL, if that helps, that's great. If someone is really visual, you may think about multiplying according to this pattern, like two interweaving circles. Okay, so let's multiply first terms. 3a times 2a is 6a squared. Then we deliver the 3a to the last term. So it's 3a times 5b, which is plus 15ab. So the first term was multiplied by each term of the second bracket. Now we go to the second term and we do the same. Therefore, negative b, because remember the term has its sign in front of it, so it's negative b, needs to be multiplied by 2a. Therefore, the sign is negative, and then the numerical value is 2 and letters a and b. Finally, we multiply the second term times the last term of the second bracket. So negative b times plus 5b, it is negative 5b squared. I intentionally used different colors so you can easily identify which terms were multiplied to obtain each product. Now, in the end, what we need to do is to look for like terms. So we have two like terms, 15ab and negative 2ab. We can collect them. So let's rewrite everything from the beginning. 6a squared plus 15 minus 2 is 13ab and minus 5b squared. And the question is done. Next example, this time we have two brackets with trinomials in each of those brackets. So since we need to multiply each term by each, we'll expect to end up with 3 times 3, 9 terms, a lot of terms. So we really have to be careful. We'll make use of colors to see clearly what are we multiplying by. The result of multiplication by the first term I'm going to record in blue. So 2x squared needs to be delivered to this term, that term, and that term. We'll obtain three products. Okay, 2x squared times 3x squared, it's 6x to the 4. Now this times this, the sign is positive, numerical value 2 times 4 is 8, and x times x squared is x cubed. My advice is, every time you multiply your terms, keep in mind this order. Ask yourself, what is the resulting sign, number, and letter? So in this case, sign would be positive times negative is negative, 2 times 5 is 10, and x squared. Okay, we've finished multiplying by 2x squared. Now we can go ahead and multiply by negative x, everything by negative x. So this times this times that, and this times that. Okay, negative x times 3x squared. Sign is negative, numerical value 3, and x times x squared is x cubed. Then multiply by the second term, sign negative, number 4, letter x squared. And again, multiply by the last term, sign 2 negative, so it's positive, number 5, letter x. Finally, we're going to multiply by 1, so this time is really easy because it doesn't change anything in the second bracket. So it will be just plus 3x squared plus 4x and minus 5. Okay, now what's left to do is to collect like terms. So starting with the highest exponent, which is just a single term, 6x to the 4. Then any term with x to the 3, so it's this one, that one, and that's all. So it's 8 minus 3, therefore it's plus 5x cubed. Now let's collect second degree terms. They are here, there, and over there. So we have negative 10 and negative 4, negative 14, plus 3, so it's negative 11. So we write negative 11x squared. And finally, linear terms, this one and that one. 5 plus 4, it's 9, plus 9x. And a free term, negative 5, stays as it was. So that will be the final answer. The following question is a product of 1, 2, 3, 4 factors. Okay, and there's two brackets. We need to multiply everything, but we can do it in many different ways. We could, for example, multiply 4x cubed times the first bracket and then multiply by the second bracket. Or we could multiply the two brackets and then multiply by 4x cubed. And the second choice is usually easier, just because the coefficients will be a little bit easier to handle when we start multiplying those two brackets first. So let's do it. Copy the 4x cubed. We'll take care of this later, and then open a bracket and multiply these two binomials using FOIL method. So 2x times x is 2x squared, 2x times negative 2 is negative 4x, then inner terms 1 times x is plus x, and the outer terms negative 2. Okay, now before I will multiply this whole bracket by 4x cubed, I would suggest to collect like terms first. So add these two linear terms. Okay, let's copy as it was, 4x cubed, and then we have 2x squared, negative 4x plus x is negative 3x, minus 2, and now we're ready to distribute the 4x cubed to the bracket, so multiply all this stuff through. Okay, 4x cubed times 2x cubed is 8x to the 5. Then 4x cubed times negative 3x, the sign is negative, number is 12, and the letter is x to the 4. And the last term, again, sign is negative, 2 times 4 is 8, and the letter is x cubed. And that will be our final answer. Since we need to be really fluent in multiplication, and also pretty soon we are going into factoring, it's a good idea to look a little bit closer at our binomial multiplication. Can we be more efficient? Thinking about FOIL stuff. When we multiply the first terms, they are usually really easy, x squared. The last terms are usually numerical, so it's also easy to multiply. That will be 10. Let's write it somewhere farther, 10. What would be the middle term? The middle term comes from multiplying the inside and outside terms. So taking the inner product, which is 5x, and outer product, which is 2x, quite often these two will be like terms. So we can actually add them in our minds. 5x plus 2x is 7x, so the middle term is plus 7x. That's a little bit faster. Instead of writing all four terms and collecting like terms, we can actually get this middle term in one step. So again, to multiply linear binomials like this, we multiply the first terms, we multiply the last terms, and the middle term comes from adding the products, the inner product and the outer product. Notice that this prepares us really well for going backwards. Imagine we'll have this problem and we would need to factor it back. So observe that the 10 is a product of 5 and 2, the last two numbers. And the 7 is actually the sum of these two numbers. Obviously, this doesn't have to be sum. It could be sometimes difference depending on those signs. But basically, we are adding those numbers with their signs. Let's see another example. Here, let's multiply the first terms, 2x squared. And the middle term comes from multiplying the inner and the outer terms and add them up. So inner is negative 3x, outer is 10x, so 10 minus 3 is 7x. And finally, negative 3 times 5 is negative 15. Really quick multiplication. We're saving quite a bit of time, and we do develop some insight that will be useful for factoring pretty soon. Now let's look at special products. Again, that will help us to multiply faster, and also it will help us to understand factoring better. So, if we need to multiply two brackets that are exactly the same, that could be written as this common bracket a plus b squared, because that's what square means. We multiply whatever's under the square twice by itself. Okay, but how much is that? If we FOIL, we'll get a times a, which is a squared, a times b, which is ab, and in the second b times a, which is also ab, and finally b times b, which is b squared. So notice that we have two of the same type of terms, ab. So instead of writing plus ab, we can at once write a squared plus 2ab, and then plus b squared. And that's the formula to memorize. This is really golden rule that is useful in every single math course. It's just a tiny bit of shortcut, but it's really useful when you multiply or when you factor things. So that's called perfect square formula, it works nearly the same for the brackets with negative inside. Let's see. If we have a minus b times a minus b, that's the same as a minus b squared. So when we FOIL it, we'll have a times a squared, then a times negative b, which is negative ab, and then in a second negative b times a, which is again negative ab. See, exactly the same terms, but this time with negative. Finally, negative times negative is plus b squared. So when we collect those two like terms, again we can write this as a squared minus 2ab plus b squared. And I wish that you memorize this perfect square formula because it's absolutely essential that you use it fluently in the future. Another important formula, it's a difference of squares. This time, if we multiply two brackets with exactly the same terms, but with opposite signs, we can make a really big shortcut in this multiplication. Let's observe. If we FOIL, we'll get a squared, and then a times negative b is negative ab, but in a second we multiply b times a, which is ab plus ab. Finally, b times negative b is negative b squared. So as you see, these two middle terms are opposite to each other, so we can cancel them. That's why the final formula is very easy. It's just a squared minus b squared. Again, really good to remember it. Difference of squares, when we multiply brackets with two different signs but the same terms, they are often called conjugate brackets. So if we multiply two conjugates, then the answer is just the square of the first term minus the square of the last term. However, when we square a binomial with a plus or with a minus, we end up with the first term square plus or minus, depending on the sign inside the bracket, double the product of the two terms, and then plus the last term square. Very important formula. Remember that when we square a binomial, we end up with three terms. So make sure that you never think of a perfect square like a square of the first term and the last term. That works only for difference of squares. We have the first and the last term squared. Perfect square will always have three terms in the end. Generally, if you raise to the nth degree x plus y, a binomial, this is not equal to just x to the n plus y to the n. That doesn't work for any n except for 1. Obviously, if n equals 1, the formula would work, as then we would have x plus y to the first power equals x to the 1 plus y to the 1, which is the same. The formula wouldn't work, though, for any other n's. It's easy to see it when we take, for example, x equals 1 and y equals 1. Then we would have 2 to the n on one side and 1 to the n plus 1 to the n, which is 2, on the other side of the equation. That's obviously it's not the same unless n is 1. So don't make this error. Perfect square results in three terms, as stated above. Okay, let's try to use those special products whenever it's possible. Obviously, it's only possible when the terms are exactly the same in both brackets. So what do we have here? In the first bracket we have 2x and 3y, in the second also it's 2x and 3y. And the signs are different. So which formula should we use? Difference of squares. So that's really easy to apply. We need to square just the first term, which is 4x squared. Remember, when we square 2x, the 2 gets squared and the x gets squared. And then minus, we square the last term, which is 9y squared. And the question is done. So it's beautiful. We don't need to FOIL anymore. We saved quite a bit of time. The next one is a perfect square of binomial. So the first formula applies. Okay, let's follow it. We square the first term. Squaring the 2x means we'll get 4x squared. Then we use the sign that we see in a bracket, which is plus. And then we need to perform this double the product form. How to remember it the easiest way? I just multiply those terms as I see them, so it's 6xy, and then I need to double it. So it's 6, double it, it's 12xy. So just the product of what you see and double it. Finally, the last term is 3y squared. So we square the 3 and square the y. Therefore, it's 9y squared. As you see, the last terms are exactly the same, but we have this middle term that is essential for perfect square formula. Okay, let's apply our formulas whenever it's possible. So first of all, check if the problem actually falls into the pattern. Do we have the same terms? Yes, we do. Do we have different signs? Yes, we do. So it's a difference of squares formula. This time, because we play with decimals, we want to be careful when we square. I'm going to just write down what I'm going to square and leave the squaring part for later so we can have a bit of time to think about it. Okay, and then it's minus the last term square, so 0.5b squared, which will be squared. So now, how do we square 0.2? Remember, when we multiply decimal by decimal, we place the decimal dot in the product by counting the total number of decimal places in both factors. So in this case, 0.2 times 0.2 will be point and then 2 places. Since 2 times 2 is 4, we write the 4 at the last place, and then we need to fill up this empty spot by 0. So 0.2 square, it's 0.04. A square obviously is a square, and then minus again 0.5 square is 0.25. And then b squared to the square is b to the 4. That will be our final answer. Now, this question is about perfect square of two terms. So, according to our rule, we should square the first term, which is easy to calculate, it's just 9x squared, right? And then it's minus double the product. So let's write it down nice and slowly. 2 times, that's double from the formula, the product of the two terms. So the first term is 3x, and the last term is 1/2 y. Obviously, we could do it in our minds if we are fluent enough, but this time we can still write it down and perform this multiplication in the next step. Finally, plus the last term square. Again, let's write it down the last term and square it, leave it for the next time. Okay, so we have 9x squared, and then we can reduce this 2 with that 2. So what's left is 3 times x times y. So it's negative 3xy. Finally, when we square 1/2, we get 1/4. So we could even write this as y squared over 4, or equivalently 1/4 y squared. That means the same. Okay, next example. Perfect square of the difference. This time we have a little bit funny expressions because the exponents are letters, not numbers. But let's stick with the rule. We need to square the first term. Let's write it down like this. Minus double the product of the two terms. Let's copy those two terms. And plus the square of the last term. This last sign is always plus. No matter if the sign inside the bracket is positive or negative, the last term is always positive in the formula. Why? Just because we are squaring, so no matter what sign when squared, it becomes positive. Okay, so how much is x to the a and raised to the power 2? Well, let's recall the rule. Power to the power, we should multiply exponents. So keep the base and multiply exponents will be 2a, not a squared, it's 2a. Minus, there's nothing to do here, just copy it, and plus y to the 2b, and that's all. Now, how can we multiply these two long brackets, three-term brackets, in more efficient way? Can we see any formula that we could apply to make our calculation shorter? Well, if we group the first two terms and treat them like one package, treat them like one term, so we'll have something minus 2 and something plus 2, the same something. Okay, therefore keeping in mind this minus and plus, and keeping the first term as x plus y, and the second term as 2, we can see that this falls into difference of squares formula. So the first term, which is x plus y square, minus the last term, which is just 2 square. 2 square is 4. Well, that's pretty nice. It's already a lot shorter, but we still need to perform this perfect square, unfold this bracket. So, perfect square, square of the first term, which is x squared, plus double the product of our two terms, so it's 2xy, and plus the last term square, y squared. Finally, minus 4. And we've done. We didn't have to go into FOIL and calculate all 9 terms and then collect like terms and come back to this answer. It could be done like that, but it's a lot shorter when we use our special formulas. So I will encourage you to use them as often as it's possible. Also, observe what we have here. Try to analyze and try to think backwards. How can we come back to this factoring stage? Because pretty soon we will have this kind of problems to factor. Next question, we have 3 brackets to multiply. Can we use any of our favorite formulas? Well, if I look at these first 2 brackets, they fall into difference of squares. So let's use it. First term square, it's 9a squared, minus last term square, it's b squared, bracket. And then we multiply by exactly the same bracket. So instead of writing this bracket again, I could write the little 2 at the top here. That means perfect square of 9a squared minus b squared. Good. Now we can use perfect square formula. So let's square the first term. Okay, let's write it nice and slowly. 9a squared is going to be squared in the future. And then minus, since this is perfect square, remember we need to think about 3 terms. So we have the middle term. Middle term is the product and double it. Product is 9a squared b squared, double it is 18a squared b squared. Finally, plus last term squared. So it's b squared squared. So what's left to do is to raise to the square those outside terms. So we have 81a to the 4 minus 18a squared b squared and plus b to the 4. And it's done. The next example, at first it doesn't look like we can use any formula. But let's see a little bit closer. Again, if I will group the first 2 terms and treat this as one package, as one term, and treat the 3z as a second term, I can really apply the perfect square of the difference. Okay, so the perfect square of the difference starts with the first term square, which is the whole package. So I need to use a bracket, 2x plus y, and square it. Then it's minus because of the middle sign. Double the product, 2 times the first term, 2x plus y, and times the second term, which is 3z. Remember, the sign is already taken care of. So we use 3z, not negative 3z. And finally, plus last term square. Okay, so here we have a little bit more to do, because now we need to square this bracket using perfect square formula again. So square of the first term, 4x squared, plus double the product, 2xy, double it is 4xy, and plus y squared. And then we need to multiply these 3 factors. So to do it in steps, maybe let's multiply 2 times 3z first and leave multiplication by the bracket for the next line. So negative 2 times 3z is negative 6z times a bracket 2x plus y in the future. Finally, plus 9z squared. Okay, so since we don't have any like terms yet, let's just arrange our polynomial according to decreasing order of exponents and alphabetical order. So it will be equal to 4x squared, then it's plus y squared, then it's plus 9z squared, and then we have plus 4xy, and then we multiply these brackets, so it's negative 12xz and negative 6yz. Final answer. In the next question, we need to calculate cube of x minus 2. Well, there is a formula for cube of a binomial, but we didn't introduce it yet. We just need to multiply. That really means that we need to multiply all those 3 brackets. However, we can help ourselves using the perfect square formula. So leave one bracket aside, and the other 2 brackets we can write as a perfect square. So let's rewrite x minus 2, and then square this binomial. It will be first term square x squared minus double the product 4x and plus last term square, it's 4. Finally, this time we really need to FOIL. There's no other way. So x times everything what's in the second bracket, it will be x to the 3 minus 4x squared plus 4x. And then minus 2 times everything what's in the second bracket. So we have negative 2x squared, positive 8x, and negative 8. Finally, we need to look at collecting like terms. So we have x cubed for sure, and then it's square here and square there. Negative 4, negative 2 is negative 6x squared, and the linear terms 4 plus 8 is plus 12x minus 8. That's all. Wow, this time we have the fourth power of p plus 1. Well, let's see how this will work. I would say rewrite this into second power of p plus 1 times another second power of p plus 1, because we know how to square a binomial easily. So apply this perfect square to the first bracket. We'll have p squared plus 2p plus 1 and another p squared plus 2p plus 1. We could use a square here, but in this case we have to FOIL anyway, so it's better to see them nice and clearly. See all those terms. Okay, and now we need to patiently FOIL everything. So first p squared times everything in the second bracket. We'll get p to the 4 plus 2p to the 3 plus p squared. Now 2p times everything in the second bracket. We'll get plus 2p to the 3 plus 4p squared and plus 2p. Finally, 1 times everything in the second bracket, so it's just the second bracket, plus p squared plus 2p and plus 1. That will be equal to, and what's left to do is just collect like terms. The fourth degree term is just 1, so p to the 4. Now the third degree terms are here and there, so we'll have plus 4p cubed, and then p squared, and p squared. 1 and 1 and 4 is 6p squared. 6 of p squared. Finally, linear terms, 2p plus 2p is 4p, and a free term plus 1. And we're done. So, wow, that was a big question. One more example. Again, 3 terms times 3 terms. Is it any way that we can see application of any of those special formulas, either perfect square or difference of squares? Well, that's maybe not so easy to recognize because the signs are totally different, right? But if we rewrite this bracket in the following form, take 5 and then take this minus outside of the bracket. So if I place a bracket here, the 2n will be the same, but this sign will be reversed into negative. How this may help me? Well, now I see 5 is the same, and this expression in the bracket is exactly the same. Okay, so we can treat the second bracket as 5 plus something, and the something is 2n minus n squared. So treat this like one term. This way we can apply difference of squares in order to perform this multiplication in a more efficient way. So difference of squares means we square the first term, which is 25, and then we square the last term. The last term must be in a bracket, so 2n minus n squared is going to be squared. Okay, so it's not so bad after all, because we just need to perform perfect square on the bracket. Copy the 25 and a minus, and then perform perfect square. Square of the first term is 4n squared, minus, double the product, it's 4, n times n squared is n cubed. And finally plus n squared squared is n to the 4. Fantastic. The last thing to do is to release this bracket and rewrite everything in opposite signs. So 25 minus 4n squared plus 4n cubed and minus n to the 4. Final answer. Here's another nice application. how our special formulas can be used to evaluate products even in our minds. If we need to multiply 298 times 302, what we could do is to rewrite this 298 as 300 minus 2 and rewrite this 302 as 300 plus 2. Well, notice that we can use difference of squares here, and that becomes the same as square of 300, which is 9 and 4 zeros, 90,000, and minus square of 2, which is 4. Okay, so we have 90,000 minus 4, so it's the same as 89,996. So to me, it's amazing. We can calculate such large number, such large product, without any long multiplication or use of a calculator. That's where I see beauty and power of mathematics. Okay, so far we've seen that polynomial functions can be multiplied. Well, let's try to generalize that. From the two given functions, we can actually create a product function. How? Well, a product function called f times g is defined in the following way. That's a definition. The value of a product function at any point x is the same as the product of the two values of f and g at the same point. So the definition is very similar to the sum of functions or difference of functions. This time we're talking about product of two functions. As before, whenever working with functions, we will be interested in domain of such a function. Well, domain of the product function is the same as the domain of the sum or difference function. It's basically the common part of the domains of the two functions that the product is built on, so f and g. If we take common part of the domains of f and g, that will be a good domain for the product function. Observe the notation. It is really essential that we won't confuse the product of two functions with the composition of functions, which is marked by a hollow circle at the middle. So the dot means product, the hollow circle means composition. Those two functions are completely different. The product is obtained by multiplying the corresponding values of each function, and the composition is taken by evaluating the outside function at the value of the inside function. So pay attention to this notation. Okay, let's practice. Given f of x, which is a linear function 3x minus 2, and g of x, which is quadratic function x squared plus 1, find the following. And now we need to ask the question, is that a product or a composition? Since there is nothing written between f and g, this is a product. So according to definition, that's the same as f of x times g of x. And now we know what's f of x. F of x is 3x minus 2. We also know what g of x is. It is x squared plus 1. And we know how to multiply polynomials, so that's not a problem. In this case, no special formula will work. We just need to FOIL. So 3x times x squared is 3x cubed. 3x times 1 is plus 3x. And then negative 2 times x squared is negative 2x squared. And negative 2 times 1 is negative 2. Let's arrange this polynomial in decreasing order of exponents, so it will look like this. Here it is. Now, let's evaluate this product function at negative 1. We could do two things. If we didn't have the first question, we can just go f of negative 1 times g of negative 1. And then plug in negative 1 into f function, which is 3 times negative 1 minus 2, and then plug in negative 1 to the g function, which is negative 1 squared plus 1, and then evaluate. Okay, how much would this be? Negative 3, negative 2 is negative 5, times 1 plus 1 is 2, so altogether would be negative 10. But since we already know what is this product function, it is actually here, we could use it and we could calculate it from the beginning like this. Plug in negative 1 to this function obtained in question A. So that will be 3 times negative 1 cubed minus 2 times negative 1 square plus 3 times negative 1 minus 2. Obviously, the answer should be the same. Let's see. 3 times negative 1 cubed, that's the same as negative 3. Then negative 2 times negative 1 square, which is 1, so altogether it's negative 2. And then negative 3, and then negative 2. Yes, it is negative 10. Obviously, we expected that it will be the same answer. So you can do it either this way or that way, it doesn't really matter. And finally, what do we have here? 2 times the value of the product function at 0. So we leave the 2 for later, and now we figure out what the product function at 0 is. Again, we can use this product function that we already have here and just replace x by 0. So all those terms will be 0, 0, 0, just negative 2 that is there. Okay, so the final answer is negative 4 here. The last application problem asks us to find the area of the given triangle. We have a triangle with given base and height, but in the form of an expression. So what's the formula for area of a triangle again? 1/2 base times height. Instead of base, we have expression 2x plus 3. Instead of height, we have expression 2x plus 4. So basically what's left to do is to multiply those expressions and see the polynomial that represents the area. Leave the 1/2 for later and then multiply the inside. Let's FOIL it. So 2x times 2x is 4x squared. Can we try to FOIL it in more efficient way? Let's see. For the second term, we can multiply the inner terms, which is 6x, and the outer terms, which is 8x. So 6x plus 8x is 14x, so we can write at once 14x. Finally, the product of the last terms is 12. Is it anything else that we can do? Well, we can multiply by 1/2, and this is actually useful because all coefficients are divisible by 2, so the final answer will be a lot nicer. That will be the expression that represents area of this triangle.